Here we come to the final part of Lecture 13. We're going to consider the temperature and pressure dependence of the standard cell voltage. Essentially what we're doing is playing around with this equation, the important equation that we derived in the previous part of this lecture, namely that delta G is minus NF E, or for standard state, delta G0 is minus NF E0. Sorry, that 0 should be up there. So what we're going to do is take what we've learned about temperature dependence and pressure dependence of delta G and just use these substitutions and make some observations about temperature and pressure dependence of E. So let's start that out. Remember we said that how G changes with temperature at constant pressure and number of moles, that's just equal to minus delta S. Well, let's substitute in minus NFE for this. So, well, actually, that's just, I got a little ahead of myself here. That's minus S. But if we look at the change, how delta G changes with temperature at constant pressure and number of moles, that's going to be minus the change in entropy. So let's go ahead and substitute for delta G, this expression here, and N and F are constant minus NF, how E changes with temperature at constant pressure number of moles, that's just equal to minus delta S, or E changes with temperature at constant pressure number of moles is just equal to delta S over NF. We could do the same thing for E0, so how E0 changes with temperature at constant pressure and number of moles is the standard entropy change for that particular reaction or process over NF. This relates just like the temperature dependence of delta G was related to delta S, E is another way of measuring delta G, so how the temperature dependence of E, that's related to delta S. That means that those equations that we used before to calculate, say, the chemical or actually the cell voltage from E0 and so on, those are all at 25 degrees. So we go back here to the standard cell potential. All of these standard cell potentials at 25 degrees centigrade or Celsius. So that means that if you're going to calculate various quantities here, yeah, you can use these numbers, but these numbers are only valid for 25 degrees. In fact, if you want to see what the E0 values would be at different temperatures, you could use this expression knowing the entropy change. So that's the first point, actually we can play around with this some more, might as well. So again, the idea is, hey, everything we learned about delta G, we can now say about E. So we said that delta G, the introchem equation is delta H minus T delta S. So we know that delta G is minus NF E. Let's make this standard state here, it'd be even cooler. Minus NF E0, that's just equal to delta H0 minus T delta S0. But look at this, we just found that delta S0 is NF, how E changes with T. So we just solve this for delta S and plug it in over here. So we have a minus NF E0, that's a delta H0 minus T, and substituting in what delta S0 was from the previous slide is just NF. And then E0 changes with temperature at constant pressure and number of moles. So what good is this? Well, I'll show you. If you measure E0, standard cell potential, as a function of temperature, you'll get a slope here, and you can calculate, and everything else is known, N and F and T are at some particular temperature, so different temperatures will give you different points here. You can calculate delta H0. That's interesting. So electrochemistry can be used to calculate enthalpies, standard enthalpies of reaction. Let's play around with pressure dependence. We'll start like we did before, so how G changes with pressure at constant temperature and number of moles is just volume, or how delta G changes with pressure at constant temperature and number of moles is how the volume changes when the process occurs. Well, let's go up here and substitute in for these, for delta G, what E is. So we can just write how, put a minus NF here, how E changes with pressure at constant temperature and number of moles. That's equal to delta V. Or how does E change with pressure? Well, this is how E changes with pressure at constant temperature and number of moles. It's just equal to delta V over minus delta V over NF. Well, that's interesting. Or similarly, how the standard cell potential changes the pressure at constant temperature and number of moles is equal to V0 over NF. So those are the kinds of things you can do. And let's see, have we done those things here? Yeah, we showed that. Let's look at this equation here. What we had was how E0 changes with temperature at constant pressure and number of moles. That's equal to the standard entropy change over NF. So let's make some finite changes. So in other words, the derivative goes to a delta, and assume we have a linear dependence. In other words, if we plot E0 versus T, we'll get a straight line. In that case, we can just replace these with delta. So delta E, so you measure E0 at one temperature and calculate another temperature. That will just be the entropy change over NF times delta T. So if you know E0 at one temperature, you can calculate E0 at another temperature approximately, where we assume we have a linear dependence of E on T, so we can just use this. So that's what that means. And we showed that by measuring the temperature dependence of E0, you could determine what delta H is. That's handy dandy. So we had how E0 changes with pressure at constant temperature and number of mole pressure. That was equal to a minus delta V over NF. And we do finite changes, etc., so that we have the change in the standard cell potential is minus delta V over NF times delta P. Note that the change in volume as a function of pressure, so you're changing the pressure here, and how's the volume change? For condensed phases, the change in volume is not very much with pressure. If you compress a liquid or a gas, a liquid or a solid, sorry, you don't get much delta V, so you wouldn't expect much pressure dependence on the standard cell potential. All right, so those are more fun things you can do once you know the key point here is something. And go away there. Let's see, key point is, there we go. Here it is. These are the key points. Somebody should write a song like Cell Potential is just another name for free energy. Hope you enjoyed this lecture, and we'll now work on lecture 14.